Alright folks, we're on to Gas Laws and Stoichiometry, the last three problems for worksheet number 8. Okay, how many liters of carbon dioxide is produced at 300 Kelvin and 99.2 kPa when acetylene is burned? Alright, so of course the first thing we have to do is come up with our balanced chemical equation for acetylene, right? And it's burned, so that means it's going with oxygen. And what do we produce in a reaction like this? Well, it's a combustion reaction, so we produce carbon dioxide and water. All right, so let's see, how do we do this? Well, we have to make sure that we balance our equation. So let's see, we've got 2 carbons on the left, we've got 2 carbons on the right, we've got 2, we're going to have a problem with our oxygens because they're odd. So let's just stick a 2 out in front of here to make an even number of oxygens. That gives us 4 hydrogens, which means we put a 2 here, which means we need 4 carbon dioxides, which means we have 8, 9, 10 oxygens, which is a 5 there. All right, so how many liters of carbon dioxide are we producing? Liters. When we have 43.65 grams, 65 grams of acetylene burning. Okay, well the first thing we have to do is figure out how much acetylene weighs. So we take C2H2, and that's 12.011 plus 1.0079 times 2, and that weighs 26.0378 grams per mole. All right, so now we have to figure out how many moles of carbon dioxide we have so that we can use PivNert to figure out how many liters of carbon dioxide we come up with. So let's start with a Stoichiometry equation where we have 43.65 grams of C2H2. We have to get rid of grams of C2H2 and go to moles of C2H2. And then we have to go from moles of C2H2 to moles of, what am I doing, carbon dioxide. Cool. All right, so our moles of C2H2 to carbon dioxide is 2 to 4. And 1 mole of C2H2 weighs 26.0378 grams. And if we do the math here, we come up with 3.3528 moles of CO2. Well, that gives us moles of CO2. Now we have to use PivNert to come up with liters. Well, since we're using liters, we want to use the 0.0821, which means we need to have our pressure in atmospheres. So let's convert that. 99.2 kPa. We convert it to atmospheres. So that's 101.325 kPa in 1 atmosphere. So we just multiply that, actually we divide that out, and that's 0.9790278 atmospheres. Again, I realize I can't carry all those, but I'm going to do it for now just to not have rounding errors along the way. 300 Kelvin, our temperature is already in Kelvin, so I don't need to mess with that. So let's see if I have PivNert, and I'm trying to solve for volume. So volume is equal to nRT over P. So my number of moles is 3.3528 moles of CO2. And my R constant is 0.0821 liters, atmospheres, moles Kelvin. And my temperature is 300 Kelvin. Nice round figure. And my pressure is, what's my pressure? I just figured out that it's in ATM up there, so it's 0.9790278 atmospheres. My atmospheres cancel, my Kelvin cancels, my moles cancel. I am left with liters, which is exactly what I want as my answer. When I multiply it out, I get 84.35 liters. And maybe it's questionable how you get, but I'm going to guess this is probably 84.4 because I can only have 3 sig figs because of this guy up here. All right, so that should give me an answer. So about 84.4 liters. Okay. On to my next one. Silicon dioxide. Oh, how nice. They gave you the equation. Don't have to worry about that. Oh, yuck. But we're collecting over water. Oh, yes, we have to do that. Let's start with that. 22 degrees Celsius. Let's bounce down, figure out what that is. 22 Celsius is 19.8 millimeters of mercury. Well, this is 19.8. They gave it to you in millimeters of mercury, so I can subtract that because this is the atmospheric pressure. So I have to subtract the 19.8. So that's going to give me 0.9, and it's going to give me 600 and... That's not right. 8 from 7 is 9. Did not do that right. 637? 637.2. Sorry, 637.2 millimeters of mercury. All right, so that's our pressure of carbon monoxide, of CO. All right, because remember, this is our millimeters of mercury of water. Right? So, because we collected over water, this is the only amount of pressure we can use. We can't use the full thing. That's the total. All right. So let's see. I'm doing this with, let's see, what am I doing? Grams of silicon dioxide will be the volume. I like liters, so I'm going to use the 0.0821, which means I have to convert this into atmospheres. So 637.2 millimeters of mercury, and I'm going to get rid of 760 millimeters of mercury and go to atmospheres. So when I do that math, I'm going to come up with 0.838421 atmospheres. Okay, let's see, I've got 22 Celsius. I add 273 to that, and I get 295 Kelvin. Is there anything else I need to convert? All right. So we're starting with this many grams of silicon dioxide. So I've done a lot of conversions, but I haven't actually done Pivnert or Stoich yet. Since I'm starting with grams and I have to figure out how many moles of carbon monoxide I have to go through my Stoich first. So silicon dioxide, how much does silicon dioxide weigh? Well, silicon is, let's see, silicon's about 32. And oxygen, I think 32.09 or something. And we're adding in the two oxygens, which is another 32. So that comes out to be 64 point something, right? Let's try that again. Silicon is 28.09. 28.09 plus 32. So that's going to give me 60.09 grams per mole. Trying to do that from memory, had to look it up. Okay. So let's go and do our Stoich portion. So we're going to start with 96.25 grams of silicon dioxide. And I have to get rid of grams of silicon dioxide and go to moles of silicon dioxide. But I have to get rid of moles of silicon dioxide because I don't want silicon dioxide. I want moles of carbon monoxide. So let's see what we have. We know that 1 mole of silicon dioxide weighs 60.09 grams. And let's see, silicon dioxide is 1 and carbon monoxide is 2. So that's a 1-to-2 ratio. So when I do that math, I come up with 3.203528 moles of carbon monoxide. Okay, so now what I have to do is I have to use Pivnert. And I'm trying to figure out the volume. So volume is going to be nRT over P. And the number of moles, which I just calculated, is 3.203528 moles of carbon monoxide. And my R constant is 0.0821 liters, atmospheres, moles Kelvin. And my temperature is, let's see, what's my temperature? 295 Kelvin. And what's my pressure? Let's see, where's my pressure? My pressure is, oh, remember we had to take out the water. So we got 637.2 millimeters of mercury, which we converted over here to atmospheres. So there's our atmospheres pressure, 0.838421 atmospheres. We check all of our units to make sure they balance. Canceling the ones that balance, we're left with liters, which is what we want. When we're all done, we calculate this out to 92.54 liters. And we might have to go down to 3 sig figs because of this 657. So we'd end up with 92.5 liters. Okay. All right, last one. All right, nitroglycerin. Guys, I'm assuming you're all familiar with nitroglycerin, of how it explodes. We're doing this in a 1 milliliter container. We're going to assume that the container does not break open upon detonation. You will find out by doing this problem why you know that it breaks up during detonation, because the pressure is so high. Okay. All right, so let's go ahead and do this. We have a sealed 1 milliliter container, and it contains 2.8 grams of nitroglycerin, which is then detonated according to this equation that you see up here. We're assuming that the temperature inside the container is going to be 300 degrees Celsius. All right. So let's go and do some conversions before we go too far. We have 300 degrees Celsius, and we know we're going to have to put that into Kelvin, so we add 273, so we get 573 Kelvin as our temperature. We also look at this as being 1 milliliter, so 1 milliliter is equal to 0.001 liters. And since we have numbers in liters, that's helpful. Let's see, what else do we have to do? We have 2.8 grams of nitroglycerin. So we have to figure out how much nitroglycerin weighs, which is this thing over here. All right, so we have to add up 3 carbons, 5 hydrogens, 9 oxygens, 3 nitrogens. I'm not going to waste your time doing that. That's 227.0935 grams per mole. So you should be able to do that on your own. All right, so now we start with 2.8 grams of nitroglycerin. And we have the mass of nitroglycerin, which is 227.0935 grams per mole of nitroglycerin. I'm just going to say Ng because I'm lazy. And we have to get rid of moles of nitroglycerin, and we have to go to moles of, what do we want to go to? This is confusing. How do we get to the pressure of all of these gases all put together? Well, remember Dalton's law? Dalton's law says all of the gases together are all treated exactly the same way. So we have 12 grams. Let me kind of come over here to the side. We have 12 grams of carbon dioxide, 12 moles of carbon dioxide, 1 mole of oxygen, 6 moles of nitrogen, 10 moles of water. If I add all those up, I get a total of 29 moles of gas. Do I care what the gas is? Not really, because all I'm looking at is how much pressure does this create. So I'm actually I'm going from 4 moles of nitroglycerin, to a total of 29 moles of gas. And again, I don't care what the gas is, so it makes no difference to me at all. All right, this is going to create 0.08939 moles of a gas. In fact, of all gases. All right. So again, I don't care what the gas is, right? But that's how many moles of gas I am going to be producing. All right. That was kind of a tricky question, right? But now what we can use is we can use PivNerd. All right. So now we can use PivNerd, nRT. So we want to figure out the volume. So the volume is going to be nRT over P. No, we don't. I want to find the pressure. We know the volume. The volume didn't change. It did not explode, remember? All right. So our pressure is going to be the number of moles, which is 0.08939 moles of a gas, times R, which is 0.0821. This is moles. And this is liters, atmospheres, moles, Kelvin. And our temperature is going to be 573 Kelvin. Right? And our volume is going to be, we said it is not changing, so it's 0.001 liters. All right, so we do that math, and we come up with a pressure of 4,205 atmospheres. Right? So folks, what that tells you is there's all of this pressure, 4,000 atmospheres of pressure, sitting inside this little container, right, which should be just blowing apart, and it's not. So, bottom line is it should be creating a huge volume, and it isn't. All right. So, needless to say, that little 1 milliliter sealed container is going to blow apart. Okay, it's not going to be able to withstand that pressure. All right, folks, that's it. Let us know if you have questions. We do have more problems if you need them to help you, so we can do some problems with you in class if you have questions. All right, and we'll see you then. Have a great day. Bye-bye.